Hey, what's up everybody? Mr. Murray here, and today we are talking about multiplicity of zeros. So first of all, what is a zero? A zero is another term for essentially an x-intercept, or aka the roots of a function, and we'll be reviewing how to find the zeros. How do you find x-intercepts? You set the equation equal to 0 or put 0 in for y and solve for the x values that make that true. Usually that would involve factoring, and in this case our equation is already factored for us, so we can jump right into that idea of then setting each factor equal to 0 and solving for x. Right, and so nice and easy here. Our first solution is x equals 0. Our second solution is x equals -2, right? Because that would just be subtracting 2 from each side. And our third solution, what makes this 0, is +3. Okay, so hopefully that is nothing new there. But now let's talk about the definition of multiplicity. Every 0 has a multiplicity. So the multiplicity is essentially how many times is that 0 a solution of the function. So for example, the first 0 of x equals 0 came from this factor of x cubed, which is really x times x times x equals 0. Or in other words, it was a solution 3 times. So it has a multiplicity of 3. And so what you're really going to look for is really just that exponent will tell you, hey, that's the multiplicity of 3. The 0 of -2 has a multiplicity of 1, because if you look at that, there was an exponent of 1 there, right? It wasn't only a solution once. +3 has a multiplicity of 2, because that's really x minus 3 times x minus 3, right? So twice. And there we go. There's the multiplicity of each one, which doesn't seem like a big deal, but what does it mean more importantly? And that's why I have the graph here shown to you, that yes, these are the three x-intercepts, 0, -2, and +3. The multiplicity tells you what the graph does at that particular 0. So let's take a look at each of these, and I'll start with all the way on the right here at +3. So at +3, it has a multiplicity of 2. And whenever it's got an even multiplicity, notice what the graph is doing at that little spot. In that little neighborhood, the graph is bouncing off of that x-intercept. It's not crossing the x-axis. It's just glancing off and staying on that side of the x-axis. So that will happen anytime, and I could just call that a bounce. That's not really a technical term, but that'll happen anytime you have an even multiplicity. And if you think about it, it's kind of like in that little brief window, in that little neighborhood, it's acting like an even degree polynomial. It's acting like a parabola, right? And so that would happen whether the multiplicity was 4 or 6 or etc. Now take a look at the next one here, -2, which had a multiplicity of 1. So right here, multiplicity tells you about the behavior. Well, in that neighborhood, it's like acting like a degree 1 polynomial, aka a line. It's just crossing straight over the x-axis in kind of a linear fashion. If you zoom in enough on that, it just looks like a line. And so I would just call that a pass-through or a crossover kind of a thing. And that will happen anytime it's got a multiplicity of 1. The graph will just cross straight over at that x-intercept, just like a line for that brief little moment. And at x equals 0, it's got a multiplicity of 3. So notice what was happening there. It does cross over the x-axis, You know, it doesn't bounce off of it like the even one did. But look how it crosses over it. It doesn't just pass over in a linear fashion. It kind of does this little behavior, which I call a wiggle, for lack of a better term. And that's behaving kind of like a cubic function in that little neighborhood, like an x to the third graph. So anytime it's got an odd multiplicity, it's going to cross the x-axis. And if it's got a multiplicity of 1, it's going to cross straight over like a line. If it's got odd multiplicity but not 1, so 3, 5, 7, etc., it's going to do this kind of wiggle, that cubic behavior. It's going to cross the x-axis, but it's going to do so in that funky little fashion there. So there we go. That's the meaning of what multiplicity tells you about a graph. It tells you about whether it crosses the x-axis or not, and if so, what kind of behavior is it doing. So if it's even, it does not cross the x-axis. If it's odd, it will cross the x-axis. 1, multiplicity of 1 crosses straight over like a line. Any other odd multiplicity, 3, 5, etc., it's going to cross over in that cubic fashion there. So that's the meaning of it. Now let's just check a few other examples just to make sure you got the idea of it. And in so doing, we're really going to review our factoring and how to find those zeros. Always a good opportunity to brush up on that, because this one is not factored for you. So our first move to find these zeros is set the equation equal to 0 and try to factor it. And first thing I can do, look for that greatest common factor, which would be x squared. And take x squared out. That is the greatest common factor. What are we left with? We will then have x to the third plus 3x squared minus 9x minus 27. Okay, now we want to try to factor this 4-term polynomial a little further. And factoring something with 4 terms, that's when we typically try grouping. So this one right here, I'm going to use these brackets. This could kind of show there's a lot going on the inside here. But I don't want to forget about my x squared. So it's right out in front, but I'm kind of done with that. So grouping, remember, typically we group the first 2 and the second 2 together, and we see if that works out. What can I take out of that first group? I can factor out x squared out of there, and that will be x plus 3. What can I factor out of that second group? I can factor out a negative 9. And then that will be x plus 3. And that tells you right there, when you have the same factor here and there, that tells you grouping is working. You're not done yet, though, because it's not in factored form until you have it expressed as a series of products. And so remember how this works here. That would be x squared minus 9 times that common quantity of x plus 3, which you can factor out. Some people like to put the x plus 3 first, some people like to put a second, whatever. But now that is factored, and it does actually factor a little bit further, because this x squared minus 9 is a difference of 2 squares. So x plus 3, x minus 3. Okay, now we are totally factored, and we're solving it for when it's equal to 0, right? So set each factor equal to 0. Should be a piece of cake, right? And from that first factor, we're going to get x equals 0 as a solution. From the second factor, negative 3. Third quantity, positive 3. And this last one here, you're going to get x equals negative 3 again. So rather than write it twice, I'm just going to say, hey, that really means I have a greater multiplicity of that 0 because it occurred twice, right? In fact, I could have taken a step and written x plus 3 squared, since there were 2 of them. So those are my zeros. And now what's the multiplicity of each one? The 0 of 0 had a multiplicity of 2 because it was x squared. The multiplicity of negative 3 was also 2 because it was 1 here and 1 here, so total of 2. The 0 of positive 3 came from this, and it only had a multiplicity of 1. So there are your zeros with their corresponding multiplicities. Also, a nice little check, notice that the multiplicities, when you add them up, 2 plus 2 plus 1 is a total of 5, and that is the total degree, that highest exponent of the original polynomial function here. If it's got a degree 5, it should have 5 zeros, and so that multiplicity should account for that. There's all 5. And if you really wanted, you could then use that to sketch the graph using what you know about multiplicity and bouncing off and all that kind of stuff. So we're going to move on though and just take a look at one more here. Let's find these zeros and their multiplicity. And so when I set this equal to 0, I've got to factor this, right? First thing I look for, greatest common factor of x. I've got x to the 4th minus 8x squared minus 48. Okay, and that now is a trinomial, and I'm trying to factor that further. But a trinomial, but this is in what we call quadratic form, right? It's x to the 4th, but you got x squared in the middle. So this can be factored the way you do a typical, quadratic trinomial, where if that's x to the 4th, then I know x squared and x squared goes here and there. And you're looking for that classic pattern of what multiplies to negative 48 but adds up to negative 8. And that would be negative 12 and positive 4. And does that factor any further? No, it does not, because that's x squared plus 4 at the end, so not a difference of 2 squares. It's a sum of 2 squares, which does not factor. So here we go, though. Time to solve this for when it equals 0. So one solution is x equals 0. That's easy enough. When you set x squared minus 12 equal to 0, that didn't factor, but it's got 2 solutions in there, right? Add 12, and now take the square root of both sides. Now, when you take the square root of 12, you have to remember to put a plus or minus out in front whenever you take the square root to solve an equation. And 12 is not a perfect square, but it does reduce, right? Square root of 4 times square root of 3, and square root of 4 is 2. So plus or minus 2 root 3. And x squared plus 4, you might spot this right now without having to do any work. But if you subtract 4 and then try to take the square root, you're taking the square root of a negative, and that's where you get into imaginary, aka complex zeros. And if you care, that's a little review there. That's plus or minus 2i. But the direction said we're only going to find real zeros. Real zeros are what would help us graph this, and I'm not going to hit the x-axis at 2i. So the real zeros are 0, negative 2 root 3, and positive 2 root 3. Right? That's plus or minus 2 root 3 is. And each one has a multiplicity. The multiplicity of 0 was 1. That came from x to the 1st. And just be careful with this here. Maybe it's obvious to you, maybe it's not. But negative 2 root 3 and positive 2 root 3 each have a multiplicity of 1. In case you were looking at the x squared and saying, hey, they each have a multiplicity of 2. No, this x squared equals 12 contained 2 zeros. One of them was 2 root 3 and the other was negative 2 root 3. So each one of them accounts for 1 of that total of 2. So they each occur once. And by the way, this 2i and negative 2i, there's the other 2 zeros that give you your 5 total zeros. But there are only 3 real zeros, each with a multiplicity of 1. And so if I were to look at that graph, I would see this graph just crossing over. Here's 0, here's negative 2 root 3, here's positive 2 root 3, say. And it would be just crossing over like a line, crossing over like a line, crossing over like a line, and doing that kind of thing. No bouncing off or wiggling or any of that kind of stuff. So there we go. There's the definition of multiplicity, how to find it, and more importantly, what does it mean in terms of the graph. If you got any questions, just ask, and we'll see you later. Take it easy.